Hello everyone. For those of you who couldn't come to today's Monday session, I'll be going through an example that is very similar to the first part of the project in terms of what skills you need to know in Matlab in order to finish it, and hopefully they'll help you through the project. We're also going to learn how to make for loops, which are going to again help us with the project, and I hope this helps. So in order to introduce all these topics, I made an example regarding first order kinetics. Don't panic about this. This is just very simple example. So we're going to be looking at reactants are going to products B with a first order kinetics. So after you integrate the reaction rate, you get this expression. So what this expression is telling us is that the concentration of the products is equal to the initial concentration of the reactants times this expression here, which is just 1 minus the exponent of the negative k times t, where k is the reaction rate constant. So now what I want you to do first is we say that the reaction rate constant is equal to 0.05 and that our initial concentration of R is equal to 2 right here. And what I want you to do is to plot the concentration of the products as a function of time, so from 0 to 100. And I give you the clue that we should make an anonymous function for P, which is depending on T, which is our time. So we already went over how to make an anonymous function, but I'm just going to do it really quick here. So the first thing that I told you before we have to do is to begin by introducing our constants. In this case, our reaction rate constant and our initial concentration of our reactants, we're going to call R naught. And then this is just this. Don't forget to put the semicolon, otherwise it's going to output to your command window, which we normally don't want. Now I'm going to make an anonymous function just as a reminder. We give it a name, then we say the @sign, and then we tell the computer what variable does this function depend on. We're just going to call it depends on time, and then we're just going to copy the function that I told you guys before, which is R naught times, and let's put the periods everywhere for now. As we go on, you'll realize that you don't always have to use the periods, but it's better that for now, as you guys learn how to use Matlab, you just put them everywhere. So you see I'll have R naught times 1 minus the exponent times negative k times t. And remember that for Matlab, there is no e caret. The right expression is exp, just like in Excel. Now we have our anonymous function, which represents our equation up here. Now we're going to plot it. To plot it, I showed you guys before, we use fplot. So how fplot works is you write fplot, then you open parenthesis, and this tells you have to put the function first and then the interval you want to plot in. So we know the function, which is capital P, and we know that the interval is from 0 to 100, because I told you to plot it from 0 to 100. To create that interval, again, you just do 0, then you do 100 in square brackets, then you close parentheses. Now let's run this code just to see what happens. So we see it's just a normal first order reaction rate kinetics. Something that I forgot to do, that you should guys try to do, is to always put clear all and then CLC at the beginning of your code, just so you delete all your variables every time you run. Here you'll highlight, because it's a comma, it needs to be a semicolon. There you go. So now, we're done with the first part, which is just plotting it for these particular conditions. Now, the second part says, now we want to study the effects of changing the initial concentration of the reactant. Plot the concentration of P as a function of time for the initial concentrations of R naught, and I give you different initial concentrations. So as you guys know from your kinetics, if you increase the initial concentration of your reactant, you will change how your curve is going to look, how your product is going to look. Of course, if you add more reactant at the beginning, then you're going to have more product. So we expect to see different graphs. Now, how are we going to plot this? We're going to use for loops, which is what we expect you to do for project 1. I'm going to walk you how to do this, but to create a for loop, the first thing you need is a for condition and an end condition. Now, we want the loop to run until we're done running all of our conditions. So we want the loop to run for r naught equals to all of our initial conditions. So this is all of this stuff. Basically what you're telling the computer is that you want it to loop through r naught and then make r naught all these different values. What does that mean? It means that the first time that I go through the loop, r naught will have a value of 0.25. Then Matlab is going to do whatever's on this line, then it's going to end, and then it's going to go back to the loop. But now, the second time, r naught is going to be equal to 1. So let's just go to the empty loop just so you guys see what's happening. So we're going to run this. We already know what this function looks like. And now let's look at our workspace. We see that as it is the first time it ran, r naught is equal to 0.25. Now if we step through the loop again, r naught changes and now it becomes 1. If we step again, it changes and now it's 2. Right here, we're looking here at the workspace. I change it again, now it's 3. I change it again, now it's 4. I change it again, now it's 5. Now that it's 5, it should end because I basically told the computer for r naught being these values, run this command. But now that r naught is not anymore, then it should stop. Now I step again and then it ends. It doesn't go through anything anymore. So this is what we're gonna use. Now, the key to do this is that we're gonna again type our function because we wanted to evaluate the function every time at a defined r naught, and now we're gonna plot it. So we can just copy and paste this code here. So one more thing is that if I run my code just how it is right now, I'm only gonna end up seeing the last plot. This is because every time Matlab plots something, it deletes what was in the plot before. In order to avoid it from deleting your previous plot, you use the function hold on. What this is gonna do is that it's gonna plot things on top of each other, plot graphs on top of each other, which is what we want and which is what you should have for your project one as well. I'm gonna slowly run this so that we see how things change. Okay, so the first part we already saw, the normal plot again. Now we get to the loop. We see again at r naught is equal to 2 because that's what it was initially. As soon as I enter the loop, it should change to 0.25. Now it's 0.25. Now, what Matlab's going to do now, it's going to evaluate the function again with the new r naught value. And it's going to plot it. Now we see, for r naught equals to 0.25, we see this orange curve here. Now we're going to run the loop again. You see, it returned because it still has more r naughts to run. Now it returns, now it's r naught equals 1. I evaluate my function again, and I plot again. And now we see our second line, which is r naught equals to 1. Now we do the same thing one more time. Now r naught becomes 2, which is the third one. It evaluates the function p. Now it plots. And you see that it plotted it on top of the other one because r naught, the value of 2, is the one we had plotted before. Now the next one, r naught is equal to 3. It plots the next one. And then we can continue to just plot the remaining. What we see here is that, first of all, through the help of hold on, we were able to plot all of them in one graph. Then that we were able to use a for loop in order to change our constant r naught. Some mistake that I've seen you guys made is that you make your variable here r naught, and that is not correct. What you're changing is the constant, but your function itself, the x-axis is still t. It's still t. What is changing is this r naught here. So your function is still a function of time. Other mistakes I've made is just forgetting to put hold on, so then you only get one graph. Other than that, I think this should be straightforward. I'm just going to show you what happens when you don't put a hold on. I'm going to clear the plot using CLF, and I'm going to run again. And you'll see that, continue, I only get one graph. and I only get one graph because I'm keep on plotting over and over and over on top of the old graph. So you only get one. Now again, if we put hold on, we run it, we get all the graphs we wanted, which is every single value of p, every single set of values of p for all the R0 functions. And this is exactly what you have to do for your project. I think for now that's it. Please let me know if you have any questions on this video, just below in the commentaries or just on the Piazza forum. Thank you.